All right, so we have discussed the the standard canon, if you will, of theorems of complex analysis in terms of Cauchy's theorem. What is it? The integral of a holomorphic function on a domain. If the function is holomorphic on the domain, the integral is 0, right? Cauchy's integral formula is very interesting. Generalized integral formula, also very neat, very neat. And so now I'm going to spend a few minutes talking about a really different idea, which is the concept. Well, this is the formal title for this, I think, more generally, is what's called Wirtinger calculus on C. And I don't know if that, I don't even know if this name is in Gamelin, but Wirtinger, or I'm mispronouncing it, of course, but so it's really something I struggled with a lot, understanding this in graduate school, because the thing that bothers me so much, let me just show you some sample calculations before I explain it, all right? So here's a typical calculation I've seen, all right? So this is unjustified. I'm just going to do it, okay? So like partial z of z bar, right, is, so you do the product rule. Partial z times z bar plus z partial z bar partial z. All right? And then the people who nonchalantly do this sort of thing and without really explaining it, they will say something cavalier like, oh, well, z and z bar are independent, so this is 0. And so what you get is just z bar. Okay. And then if you're like me, people who use words, you expect those words to have meaning. And so this expression, oh, z and z bar are independent, this is a hard pill for me to swallow, because I know that if z is equal to x plus iy, then z bar is equal to x minus iy. In other words, if I know z, it uniquely fixes what z bar is. That does not, to me, seem like something that is well described by the sentence z and z bar are independent. Right? So, and yet there's a large community of people who say these things and mean what they say. So I guess the question is, what's the rest of this sentence, unless we were to just dismiss these people as cranks, and I wouldn't do that. The question is, what are they not saying? So let's talk about it. First of all, how do we define partial z and partial z bar? So let me show you some formal nonsense to define them. You're like, so how do you define formal nonsense? Well, what I mean by formal nonsense is that the calculation I'm doing is not technically justified by the calculation I'm doing. So, all right, so this partial z, all right, we could look at as partial x partial z, partial x, plus partial y partial z partial y. And partial z bar, that's going to be partial x partial z bar, partial x, plus partial y partial z bar, partial y. And the reason I say this is formal nonsense is, what do you mean that there's a chain rule for partial z and partial z bar? How can this be? And why should the chain rule for a complex variable z and a complex variable z bar be expressed in terms of real partial derivatives. That's very odd, right? But suspend your disbelief for a moment here, and let me remind you how x and y and z bar are related. You actually can almost see it up here with these two equations, right? See these guys right here? This and this. If we solve those, what happens if we add? Z plus z bar is what? Yeah, so x is equal to 1/2 of z plus z bar, right? And y is equal to 1/2i of z minus z bar, right? So if we solve these equations for x and y respectively, we get that. Of course, you recognize that. That's the real part of z, and that's the imaginary part of z. Those are the formulas for those. But, and I have written where I ought not write. Oops. Because I want to continue my formal nonsense on the same line. So, All right. And so what is this equal to? So what would partial x partial z be if you're willing to suspend disbelief about this not making sense? Surely it should be 1/2, right? And partial y partial z, looking at this, should be 1/2i. And if we look at z bar, we again get 1/2. But we get minus 1/2i, partial y. So in another notation, we could write this simply as 1/2 partial x plus I partial y, and 1/2 partial x minus I partial y. All right. So how do you fix formal nonsense, like logically? Well, you say it's not a calculation. You say it's a definition. So definition. Definition. Partial f partial z is equal to 1/2 partial f partial x minus, oh, did I put a curses? I'm a dummy. Look, I brought the 1/i to upstairs, right? That was a minus. This was a plus. I'm sorry. Yeah. So partial f partial x minus I partial f partial y, and partial f partial z bar is 1/2 partial f partial x plus I partial f partial y.
So we went from saying formal nonsense to just
Yeah, this is, I'm giving you definitions. So in other words, the partial derivative with respect to z is 1/2 partial x minus I partial y, and partial z bar is 1/2 partial x plus I partial y. If you want to look at them as operator equations, we could do that. There they are. Okay, so what's going on here? What good do these do? Well, let's kind of work it out. All right. So for a function of two variables, right? So let's talk about the chain rule. If we have a function which goes from, let's say, R2 to R2, right? And we have another function, gamma, which goes from, let's say, R to R2. And we're thinking of these R2s as complex numbers, all right? All right, we're thinking about these as complex numbers. Then we can think about f composed with gamma as a mapping from R to R2, right? And so we can consider the time derivative of f of gamma of t. Right? And in calculus 3, we consider such derivatives, and we prove that the partial derivative, like the derivative of this, is given by the following chain rule. It's partial f, partial x times, let me say gamma. If you don't mind, I'm going to use the usual notation. Gamma is x comma y. So like I can write this as dx dt plus partial f, partial x, partial y, dy dt. So far, nothing. I mean, I can be more explicit. I don't want to write the full formula here. I'm being lazy a bit in this expression. Like in more detail, that is the gradient of f evaluated at gamma of t, dot product with the velocity vector d gamma dt. So I'm suppressing the curve dependence on the partial derivatives, and I'm using notation and using x and y for the component functions of gamma as well. Yeah. Let's take our definition, though, and take another step. This definition, let me state a lemma. We can go a little bit further here, right? See, we could solve for partial x and partial y. What happens if you add these operator equations? You add the operator equations, the partial y's cancel, and so you get partial x plus partial x divided by, you get 2 partial x over 2. So you get, partial x is what? Partial z plus partial z bar, yeah? And how about y? Partial y is equal to what? Same thing, but with I. Yeah. You want to subtract the top one from the bottom one?
Yeah.
So if we do that, we get minus 2. Well, we get minus I, right? Minus I partial y is partial z minus partial z bar. Yeah. But just subtracting. Which, of course, gives us that partial y is I times partial z minus partial z bar, right? Because when we multiply by I, we get minus I squared, which is 1. So that's what we get, yeah? So go back up to our real chain rule now and rewrite the real chain rule in terms of, this lemma, right?
The real chain rule here?
Yeah, let's change our partial f, partial x, rewrite it in terms of z and z bars. Right, so we got.
Plus I partial z minus
All right. And then let's see here. So what we have is, I'll rewrite it in the bigger notation, partial f, partial z times what? Times dx dt plus I dy dt, yeah? Then plus partial f, partial z bar times what? Times dx dt plus what? Or minus what? Let's see here. Ooh, I've got. I guess I have to say minus I dy dt, don't I? me double check this. This is actually, some of these calculations are in, oh yeah, that's right. I'm actually deriving formula 8.3 on page 126 of Gamelin. What page number did I just say? What? 126, right? Okay, yeah. Okay, so what are we looking at here? We're looking at partial f partial z times d gamma dt plus partial f partial z bar times d gamma dt conjugate. And, you know, to be clear, both partial f partial z and partial f partial z bar, these are both evaluated at the gamma of t. Now, did I say that this function was complex differentiable? Did I say that this curve, you know, was in some, I didn't say anything. I mean, I'm just assuming that f and gamma are smooth functions. So I've not assumed complex differentiability. This is more general than that. And so what I would say is that what this partial z and partial z bar is just a complex notation for a particular linear combination of real derivatives. In other words, when people say z and z bar are independent, what they really should say, they're independent. The rest of this sentence that sometimes people don't say is as real variables. And that's still not quite right, but that's closer to the truth. I mean, really, you're picking a different basis for the complex plane, and you're using coordinates with respect to that different basis. You know, these are, I think z and z bar are they're coordinates. I think they're Cartesian coordinates for a different choice of basis on the xy plane. I guess you could ask that question. If your coordinate map, so our coordinate map, like phi of, you know, phi of z is equal to x, it's equal to x plus y, comma, x minus y. This is so like, I still don't think I'm quite saying it right. Curses. I might still, let me not, let me just say that's a conjecture. Let me not try to work that out right this minute. I've deceived myself on these things before, so let's stick to what I know for sure. I think that's true though. All right, let me spend the rest of our time on things I know for sure. Okay. One thing I know for sure is that if f is complex differentiable, then this formula becomes more interesting. So if f is holomorphic on the complexes, right, then what do we know? Cauchy-Riemann equations hold, right? Say what? They say partial f partial x is equal to I partial f partial y. Is that true? I'm trying to remember. No, I should say other way around. I should say partial f partial y is equal to I partial f partial x. We could say that. Okay. So if you know about the differential, you know, the way I see that. So if you haven't studied A calculus, so you don't ignore this comment at the moment, but df of I is I times is df of 1 times I, right? df of I, that is partial f partial y. df of 1, that is partial f partial x. If we're using 1 as the first basis element and I as the second one. So, that's how I remember where the I goes in this formula. And, because you always have a choice, plus or minus I there. All right, great. What does that say about partial f, partial z? What was it? It was 1/2 partial f, partial x minus I partial f, partial y. So what do we got? We have 1/2 of I partial f, partial, excuse me, blah, blah, blah. Okay, so I guess, my bad. There's two different ways you can go here. The one is just to use what I have in the box. And that would give us, partial f, partial x minus I times I partial f, partial x, because that is this, right? Which gives me what? I squared is, minus I squared is 1, so we get twice, divided by half, we just get partial f, partial x. Which makes a lot of sense, because this, remember, is what we also said was f prime of z, or df dz, if you want me to complete this circle of notational jibber-jabber. I am making a distinction between d dz and partial partial z. Again, partial z is just a sneaky notation for a particular linear combination of real derivatives.
Okay, how do you get from partial f, partial x? Like,
Oh, that's from before. That's what we said. The complex derivative. This is the Cauchy-Riemann equations say that. So.
yeah, okay. Partial
I mean,
x is f prime.
we had a theorem before, right? And a theorem said that if f is holomorphic, then df dz is equal to partial f partial x. And you could also write it as, goodness, I can't remember. Well, let me figure it out here right quick. So partial f partial x, of course, is ux plus I vx. If I want to convert those to y derivatives, what do I got? Ux is equal to vy, and vx is u minus uy, right? So this is equal to minus I uy plus I vy, which is minus I partial f partial y. That was from before. And you notice that if we had instead solved this for partial f partial x equals to minus I partial f partial y, then when we plug in, when we eliminate partial f partial x for minus I partial f partial y, we would have gotten two copies of that. So we'd have gotten, we'd have gotten that this is, yeah, this is also equal to minus I partial f partial y if you want. But I prefer the partial f partial x because, simple. So for a holomorphic function, number one, the partial derivative of the holomorphic function with respect to z is just df dz.
Yeah.
How about the anti-holomorphic derivative? By the way, this is called the anti-holomorphic derivative.
And just to be clear, that means the antiderivative is on holomorphic domain.
It does not mean the antiderivative on a holomorphic domain. It means not even close to that, no. But that is a reasonable interpretation of the words. But this is one of those times where the words we're using don't mean quite what you want them to. So partial f. Nice try, though. I like that. That's a new question. So partial f partial z bar is going to be 1/2 of partial f partial x plus I partial f partial y. by definition of z bar, partial z, by definition of the anti-holomorphic derivative, plus instead of minus. And what happens when I apply the Cauchy-Riemann equations to that?
Partial f, becomes minus I partial f y. Is that 0?
Yep. And for this reason, this gives us the claim that people who know what they're doing often throw around, which is that is this. F holomorphic on D means F is function of Z alone. This sentence, F is a function of Z alone, what does that mean? That means that partial F partial Z bar is 0. What is partial F partial Z bar? What does it mean to say that the anti-holomorphic derivative of F vanishes? What does that mean? That means the Cauchy-Riemann equations hold. It's just an elegant notation for expressing the Cauchy-Riemann equations. It says that particular linear combination of real derivatives vanishes. That is the Cauchy-Riemann equations. This is pretty cool, right?
Yeah.
And just another way of looking at things, but it's really nothing but a new notation for things we already know.
Yeah.
Yeah? But now if you look at,
I just like the way where we came from.
so now applying this to, let me call this thing here, let me call all this star. So look at star in the case that F is holomorphic. What does it give you? What happens then? Well, in that case, you know, we have ddt of f of gamma of t is what? I'll write down star again, partial f partial z, d gamma dt plus partial f partial z bar, d gamma bar dt. Right? And so what we just got done saying is that partial f partial z bar is 0 for a holomorphic function, and partial f partial z is df dz. So we have df dz d gamma dt. Or to be more explicit, what this is f prime of gamma of t times d gamma dt. I believe we derived this earlier in the course when I talked about conformal maps. Or at least I told you it was true back then. Now here's I've derived it now. Yeah, I've derived it in a more complicated way than I need to, because this derivation also includes the story of the anti-holomorphic part. But anyway, here it is. This is the conformal, basically the conformal condition, because it says, you know, that the tangent of the transported curve, f composed with gamma, right, the tangent of that is related to the tangent vector of the original curve, right, which would be this guy, which if I use the prime notation, this is just gamma prime of t, right? So the original tangent vector, gamma prime of t, has direction gamma prime of t. Let's say t equal to 0, gamma prime of 0. The new tangent vector has direction f prime of gamma of 0 times gamma prime of 0. So in other words, the direction of the transported curve is just related to the direction of the original curve by multiplication by a complex number. And if that complex number is non-zero, all different tangent vectors get multiplied by that same non-zero number, which means that the angle between tangent vectors is preserved, right? That's that conformality, right? So like, if this is my gamma 1, and this is my gamma 2, right? And they intersect here at time 0, and then you look at corresponding whatever. This is maybe the transport of gamma 2 and gamma 1. So this is like f composed with gamma 2, f composed with gamma 1. we have that the original tangent vector would have been like gamma 1 prime of 0. That moves over here to f composed with gamma 1 prime of 0. And the original tangent vector to gamma 2 would have been gamma 2 prime of 0. I'm assuming that they intersect at time 0 just for convenience. Gamma 2 prime of 0. And then over here, this would have been f composed with gamma 2 prime of 0. But if f prime of gamma of 0 is equal to c, this is equal to c gamma 1 prime of 0, and this is still equal to c gamma 2 prime, rather. Gamma 1 prime of 0. So the angle between gamma 1 prime of 0 and gamma 2 prime of 0 is the same as the angle between the composite with gamma 1, like f composed with gamma 1, f composed with gamma 2, because we're rotating them by the argument of c in both equations, right? They could be stretched out or compressed if c has modulus which isn't 1, but there it is. So equation 8.3 reduces to the statement that f is a conformal map, if holomorphic implies conformal, right? But the other thing, I don't think Gamelin actually talks about this, but what would it mean then if you had a mapping that had partial f partial z is 0? What would that be? So here's a weird question. What does partial f partial z equal to 0 indicate? So first of all, that would say what? That would say that, that would literally mean 1/2 partial f partial x, and how did it go? Minus I partial f partial y is equal to 0, right? So this would be, let me go to the u v notation. So this would be, give me like ux plus I Vx is equal to I times Uy plus I Vy. Agree? And so let's see here. Of course, this would give us IUy minus Vy. So we have the equations Ux is equal to minus Vy, and Vx is equal to Uy. Which is what? It is not. The Cauchy-Riemann equations are Ux equals to Vy, and Vx is equal to minus Uy. So if we look at the Jacobian of u plus iv, remember it's ux, vx, uy, vy, yeah? And so basically, this set of equations means that the matrix has the pattern A, B, minus B, A, right? That the Jacobian matrix would have that shape if that's the Cauchy-Riemann equations. But for this bizarro world set of equations here, this one, we'd have the pattern what? Ux is equal to minus, so I got like an A here, I got a minus A here, right? And I've got BB. So what's the determinant? What's the determinant of such a, if this is M, let me call this, I'll call this M and I'll call this N, just for the sake of notation. What's the determinant of M? What's the determinant of N?
That would be minus a squared minus b squared.
Yeah, minus a squared minus b squared. And the other one, of course, is a squared plus b squared, right? So the determinant of the Jacobian of a conformal of a holomorphic map has this pattern a squared plus b squared. In fact, when you look at what it is, the determinant of the Jacobian of a the determinant of the holomorphic, good grief, the determinant of the Jacobian of a holomorphic map is it's ux vy minus uy vx, but that's equal to ux squared plus vy squared, which is, by the way, just the modulus of f prime of z squared. So like the determinant of the Jacobian of a holomorphic map, this is f holomorphic. Sorry, my color coding has degraded. Is that, what would the, so here, what's the determinant of the Jacobian of an anti-holomorphic map? Let's say that this defines definition f anti-holomorphic, okay? That seems fair, doesn't it? Because if a holomorphic map has partial f partial z bar is 0, surely an anti-holomorphic map should have partial f partial z be 0, right? So the determinant of an anti-holomorphic map, what would that be? It's the determinant of, ux, well, let me just, it's still, so it's still ux vy, it's still ux vy minus uy vx, but the difference is now vy was minus ux, right? So I got minus ux squared minus vy squared, I believe. Vx.
It's u minus uy squared minus bx squared.
Minus uy squared minus vx squared.
Bx is equal to minus uy, and uy is equal to bx. Minus by,
Mm-hmm.
dy. It's minus vy squared minus ux squared.
You want minus vy squared
Yes.
minus ux squared?
Yes.
Hmm.
You can change if you'd like.
No, that's fine.
That would be ux minus.
But, the larger point here is that if the derivatives are non-zero, this is less than 0. And the theory of, calculus of the plane says that if the determinant's negative, that map is reverses orientation of tangent vectors. In other words, if one vector is related to the other by a clockwise rotation, then their images are related by a counterclockwise rotation. That's what we mean by oriented. It also means that if you look at a simply connected region, the inside will be flipped to the outside by such a map. So of course we can use the star equation and see that if we have an anti-holomorphic, so if f is anti-holomorphic, right? Then if we look at the derivative of f composed of gamma of t, what happens? So now the partial f partial z term drops out, right? And we just get partial f partial z bar times what? D gamma bar dt. And so let's see here. In other words, we get so like if suppose gamma 1 of 0 equals to gamma 2 of 0 as we have, yeah? And we consider f composed of gamma 1 prime of 0. We get, and let's let partial f partial z bar of gamma 1 of 0 equal to c, right? So we get like c times gamma 1 prime of 0 conjugate, and equals c times gamma 2 prime of 0 conjugate. So let's suppose that gamma 1 of 0 is like b e to the I theta 1, and gamma 2 of 0, b1, b2 e to the I theta 2, just to give them, suppose that's their polar form, yeah? So what you got here is you've got c b1 e to the minus I theta 1, and this would be c b2 e to the minus I theta 2. And so let me just kind of hazard a picture at all this. So originally we have, these are the primes, my bad. So originally we had, let's say, try to make my life easy enough. So originally we had perhaps this is my gamma 1 prime, right? And maybe this is my gamma 2 prime. So this one's at theta 1, this one's at theta 2, right? And then they map to what? Tangent vectors. So you can ignore the c and the b1, the c and the b2. These are just magnitude. We don't care about that. I'm interested in direction. So minus I theta 1 and minus I theta 2, like that, yeah? So this is the direction of f composed with gamma 1 prime of 0, f composed with gamma 2 prime of 0. That's what's happening here under the anti-holomorphic map. So check it out, right? It took a counterclockwise rotation from 1 into 2 to start with, but the images, it's clockwise. So counterclockwise, clockwise. It flipped them over. So on the other hand, anti-holomorphic maps still have a lot of structure, right? Because it's not just any old which way that the angles are going. The magnitude of the angles, difference between the angles, like there's still something very strong about this structure, but it's not quite as nice as holomorphic, right? And there are, of course, theorems that you can state about anti-holomorphic maps. Let's look at Cauchy's theorem for an anti-holomorphic map. What's it look like? What was Cauchy's theorem for a holomorphic map?
Let the bounded domain piecewise smooth boundary if f
Mm-hmm.
of d is holomorphic and continuously differentiable in d and extends continuously on the boundary, then the integral the integral around under a circle 0.
The integral around the
Yeah, that was Cauchy's theorem. So Cauchy's theorem said that the integral around the boundary of a holomorphic function, if it's holomorphic on the domain, then the integral around the boundary of that domain is 0.
Ooh, but we don't have inside and outside. Inside and outside are flipped, aren't they?
Don't worry about that.
Oh.
So it's not like that. But yeah, I hear your, yes. That is exactly the kind of thing we'd have to think about if we pursued this line of action further, yeah? Like if you tried to figure out anti-holomorphic analogs of other theorems, then yeah. Honestly, Audric, it's not something I've thought too much about. So let's try out for a similar theorem. Let D be bounded, and F anti-holomorphic on, D tilde, which contains D, all right, D tilde domain. In other words, let's suppose that F is anti-holomorphic on a set a little bit bigger than D, all right. Then the integral over the boundary of D of F, let's see here. F dz is what? Okay, so here's what we got to do. We're looking at the integral over the boundary of D of u plus iv times dx plus I dy, right? Going back to that notation. So then what? See, this is the integral over the boundary of D of u dx minus v dy plus I times the integral over boundary D of u dy minus, or rather plus v dx, yeah? We're going to assume f is continuously differentiable just for the sake of not going nuts here. Right? We're going to assume Green's theorem applies, okay? Which is not an unreasonable assumption. So what would Green's theorem say for both of these?
There's qdx and then there's pdx.
Right.
So you get the double integral
Mm-hmm.
of q partial x, partial q partial, sorry,
Oh.
p partial x.
Sure, I'll write it that way. So qx minus py dA, right?
Yeah, and then
Plus I, yeah. Qx minus, these are different q's, right?
yes.
I'll call these tildes. There we go. Now they're different, see? And of course, this is the integral over D, not boundary of D now. Green's theorem, right? Now, so Q here is V. So we've got minus Vx. P is U, so that's minus Uy dA, right? Plus I integral. Q here is V, so that's Vx minus P here is U minus Uy. We're assuming that this is a anti-holomorphic function. So we have not the Cauchy-Riemann equations, we have Ux equals to minus Vy and Vx is equal to Uy, right? For anti-holomorphic function. So these are the, if you like, they're the anti-holomorphic Cauchy-Riemann equations. I'm not sure that's what people, well, anyway, but you got the idea. These are the conditions that are holding for this anti-holomorphic function. How does it simplify? Does it simplify? What we got?
0. 1.
Really?
Y is equal to bx. Ooh, that's 2bx. No, wrong thing. Let's try that one. Oh, that's still 2. Still uy. Wait. Bx minus uy is just minus 2 v
No, I do think you're right. I think this one is 0.
That one's 0, yeah.
But this one,
Now it's 2 ui or 2bx, depending on how you, or minus 2 ui or minus 2bx, depending on how you slice.
we'll keep the v, partial d minus 2 vx dA. Shnikes.
We go wrong.
Yeah, I should have. I'm making my life too hard, and I feel like I've. Oh, let's see here. Look, this was wrong. This was supposed to be. I did this one wrong. Yeah. Look, the q is u, so I'm supposed to have ux, and then p here is v, so minus vy.
So that gives minus 2 ui.
Yeah, plus 2i integral. What would you say? Ux. Yeah. I'm keeping the u. I'm keeping the ux. So ux dA. All right. So in other words, we have I integral d of 2 times ux, times 2 parentheses ux plus I vx dA.
Missing a minus.
Am I? Because I put I squared is minus 1, so that's why I traded this minus 1 for these 2 i's. So the reason I did that, of course, is now we've got I integral of 2 times partial f partial x dA. But since we're assuming this is anti-holomorphic, what was the how did the what was partial z bar? Partial f, partial z bar, what was it? Partial f, partial x, minus I, partial f, partial y, is that right? A plus, right? Oh, curses. Sorry, I've gone over time.
Yeah, minus partial f partial z bar.
Yeah, partial f, partial z bar, it's got the plus in it, right? Yeah, because the minus was in the partial z. But the other thing is the for a holomorphic function, but we're on anti-holomorphic. And listen, so the what did you get here? What was the equation? I partial f partial y was what? It was partial f partial x, right?
Yeah.
So this is twice partial f partial x. But there's a half, right? I forgot my half.
Yeah, it's a 1/2.
So partial f partial z bar is partial f partial x in the case f is anti-holomorphic.
So that implies that I double integral
Mm-hmm.
2 partial f partial z
not equal to 0, but the integral over the boundary of d of f dz is just equal to I times the double integral of the partial derivative of f with respect to z bar dA. So this was not 0, right? And yeah. So this is the Cauchy's theorem, the anti-Cauchy theorem. But in my heart, Audric, I don't think this is really the proper anti-Cauchy theorem, because I don't feel like it's fair to integrate an anti-holomorphic function f with respect to dz. You really ought to be integrating it with respect to dz bar. That will change things because it introduces a minus sign asymmetrically only into the differential, and that minus sign will compensate the other minus signs. So I think there's a theory of complex analysis for anti-holomorphic functions. But that's kind of like the upside down. We don't like to think about it. So what's Stranger Things? It's just an expression people use. Sorry.